Hi, my name is Stephen McKean. I'm a graduate student at Duke University. My advisor is Kass-Wickelgren. And today I'll be talking about my research from the perspective of the Brouwer degree, especially the Brouwer degree in motivic homotopy theory. So the Brouwer degree, as you might teach your students in a first course in algebraic topology, assigns an integer to a map from the n-sphere to itself. You can compute this locally using differential topology. So you take the Jacobian of your function, and everywhere that your function vanishes, you look at whether that Jacobian was positive or negative. You sum up those plus ones and minus ones, and that gives you the Brouwer degree. You can also compute it locally using an algebraic formula due to Eisenbud, Levine, and independently Khimshashvili. And what Eisenbud, Levine, and Khimshashvili do is they write down a bilinear form over the real numbers whose signature computes the Brouwer degree locally at a point. And an application that you might teach your students is that you can prove the Brouwer fixed point theorem using the Brouwer degree. So there's an analog of the Brouwer degree in motivic homotopy theory called the A1 degree, due to Fabian Morel. And again, you take a function from the n-sphere to the n-sphere. Here we have a more complicated notion of what an n-sphere should look like. And instead of assigning to it an integer, you assign to it a bilinear form, or rather an isomorphism class of a symmetric non-degenerate bilinear form. So GWK, the Grothendieck-Witt group over a field K, is just the group of such isomorphism classes. You can compute this degree globally in dimension 1 using a result of Kazanav, or you can also compute locally using an algebraic formula due to Kass-Wickelgren. And what Kass-Wickelgren actually show is that this bilinear form that Eisenbud, Levine, and Khimshashvili computed, rather than taking the signature to obtain the Brouwer degree, you keep track of its isomorphism class, and this computes the local A1 degree. So this is a very nice result. And applications, there are a lot of applications of the A1 degree, especially in enumerative geometry and also in algebraic number theory. And these are the reasons why I'm mostly interested in the A1 degree. So I'll now talk about some of my results in the subject. As I mentioned, Kass-Wickelgren give a formula using the work of Eisenbud, Levine, and Khimshashvili for the local A1 degree at a point, but there are some restrictions on this result. So when you're computing this local degree, the point at which you're working either needs to be defined over the base field K, or your function needs to be tall at this point. But there are a lot more functions and types of points out there. They're non-rational points that we're interested in. And so we'd like to have a more general way of computing this local degree. And in work with Thomas Brazelton, Robert Birkeland, Michael Monteiro, and Morgan Opie, we show that this sort of idea works at points with separable residue field over the base field. So what this result says is that if P has separable residue field over the base field, you can compute the local A1 degree at this point by base changing to the field definition of your point, computing the local A1 degree rationally using this work of Kass-Wickelgren, and then transferring back down using the field trace. In ongoing work that's soon to be released with Thomas Brazelton, we study the same sort of idea now for simple extensions instead of just for separable extensions. And in dimension 1, we show that there's a similar way of lifting and transferring to compute the local A1 degree in a rational way. The lift and transfer, these might look a little bit different than just the field trace and the base change that you see for separable extensions. And an application of this, in this paper of Thomas Brazelton and mine that we're writing up right now, we show that trace forms of field extensions are actually A1 degrees. So if K is a number field over the rational numbers Q with minimal polynomial M, and if P is a root of M, then the trace form of this field extension is the local A1 degree of M prime times M at P. So I also have some work on algebraic formulas for the A1 degree. As I mentioned earlier, Kass-Wickelgren give us a way to do this for the local A1 degree at certain types of points. And Kazanav gives us a way of computing the global A1 degree in dimension 1 using something called the Bezuschen. With Thomas Brazelton and Sabrina Pauli, we generalize both of these results by showing that the multivariate analog of the Bezuschen can be used to compute the local and global A1 degree in any dimension. And something to point out is that there are no restrictions on P in the local case. So we no longer have to worry about whether our extension is separable or inseparable, or if the point P is actually K rational. This formula will work in general. It also works in any dimension rather than just in dimension 1 as Kazanav's result. And then finally, this is truly computable in that we've written down a Sage implementation for this and put it on GitHub. So if you have a function that you want to compute the A1 degree of, whether locally or globally, you can plug it into this Sage code and it will compute it for you. And an application of this, I show that the famous Jacobian conjecture can actually be phrased in terms of the Bayesian. So the Jacobian conjecture says that if I have an endomorphism of affine n space, whose Jacobian is a non-zero constant, then that function should be invertible, at least in characteristic 0. And using some ideas in this paper with Thomas Brazelton and Sabrina Pauli, I show that you can rephrase this in terms of some description of what the Bayesian should look like. And finally, another class of applications of the A1 degree are in enumerative geometry. So the Enriched enumerative geometry program is an active area right now. Classically, enumerative geometry looks at algebraic varieties over algebraically closed fields and counts them in some sense using integers. Enriched enumerative geometry works over more general fields and gives bilinear form-valued counts. And these bilinear form-valued counts carry information about counts over other fields. So taking the rank of your bilinear form should recover complex information, the classical results that you've seen. Taking the signature will recover real enumerative results, which exist in the literature oftentimes. But then other invariants of bilinear forms will tell you enumerative results over fields that typically aren't considered in the literature. This really relies on the fact that the A1 degree is something topological, that it's not just a commutative algebraic construction. Really, what we want to use is that the A1 degree can be used to compute an Euler class. These Euler classes have nice invariance properties, which we use to get our global invariant count. And the local A1 degree carries geometric information about the geometry, the algebraic geometry question that we're looking at. And so we play these ideas off of each other. We have local information that is geometrically interesting and global invariant information coming from an Euler class. So a few results in the area that I've been involved with. I have a paper that gives a description of what Bézout's theorem looks like from this perspective. The intersection multiplicity that you usually use to treat Bézout's theorem over the complex numbers is replaced by a sort of volume that's measuring how hypersurfaces are intersecting, looking at their gradient directions at intersection points. With Cameron Darwin, Igor Galimova, and Pam Gue, we also do a similar construction for conic curves meeting 8 lines in P3. And again, the local information keeps track of how these conics are meeting the 8 lines at each of their intersection points. And then finally, I have some ongoing work on the circles of Apollonius from this perspective, which give new ways of measuring or considering how circles are tangent to given 3 circles. So there's a lot to be studied in this area, and a lot of my future work will be relating to enumerative geometry over, say, rings or in kind of more general contexts. Thank you for listening.